Welcome fourth graders to the Dallas Independent School District's STEM Environmental Education Center. And we'd like to give a special welcome to a number of schools who are with us this afternoon. First, we have the fourth graders from the Marsalius STEAM Academy. We also have fourth graders from Elm Creek Elementary in the Southwest Independent School District. We have students all the way from Kansas from Amanda Arnold Elementary School in the Manhattan-Ogden Independent School District. And last but not least, we have the girls from the Solar Preparatory School for Girls right here in the Dallas Independent School District. Thank you all so much for joining us this afternoon. We wish you could be here in person, but we'll do our best to help you feel like you're here during a virtual field trip this afternoon. If you are watching this and have not registered for today's field trip yet, you can still do that by going to www.tiny.cc/EEC register. And there you can get yourself or your class registered for today's field trip. We just use that information for our attendance purposes. And this afternoon's field trip is going to be all about force and motion. During this virtual trip, students will discover that energy exists in many forms and can be observed in cycles, patterns, and systems. Students will observe a descriptive investigation to explore the effect of force on an object. So we're going to start off today by exploring pushes and pulls with Mrs. Fuller. After that, we're going to explore the force of gravity with Ms. Ramirez. After that, we're going to explore friction with Ms. Nash. And last but not least, we're going to explore magnetism with Mr. Monroe. While we're doing all of that, you can ask us questions, and we encourage you to ask questions. But since this is a virtual field trip, the way you ask questions is by going to www.tiny.cc/EEC-question-answer. And there you'll fill out a very short form and submit your question that you have for us regarding force and motion. You can ask as many questions as you like, and we will do our best to answer all of them in the time that we have with you this afternoon. So let me stop sharing my screen here, and we're going to get started with the investigation of pushes and pulls with Mrs. Fuller.
Good afternoon, boys and girls. My name is Mrs. Fuller, and this is Lauren the chicken. We're going to be talking about energy and about force today. And when we talk about energy, energy is the ability to do work. And so we get our energy from a lot of different places. We have light and heat energy from the sun. We have in the middle of the sun, we have nuclear energy in the form of fusion. We have all different kinds of energy. The sun is the source of most energy for our planet, and it fuels photosynthesis, which is the most important chemical reaction on Earth. Now, when we talk about force, we're talking about push and pull. So this little segment is on push and pull. Let me hold that up so you can see that, push and pull. So when we say push, push is moving things away from us, and pull is moving things toward us. And one thing that you need to keep in mind is that forces cause change. Now I've got Lauren Chicken up here because she did a good job today. She laid an egg. Lauren's an Araucana chicken, and so she has these kind of olive green eggs, and she pushed it. She pushed it away from her. She pushed it out of her body so that we could have an egg omelet tomorrow morning for breakfast. That's real nice of her to do that for us. I'm going to put her down. And we're going to talk about other ways that we experience push and pull. So the first one is something that I know you're all familiar with, is a dust mop. We all have to push these around the house to get rid of the feathers in our house. And this is a Swiffer dust mop. This is one that you push, and you push it around the house to pick up any dust bunnies or any feathers. And you also have to pull it. If you push it underneath the couch, you have to pull it back. So push is away and pull is toward. So that's a good example of a tool that uses both push and pull. And there we go. Another one is we can exhibit push and pull a lot of different ways. One way is direct contact. That's what the Swiffer was. I had direct contact with my hand to push it around on the floor and to pull it back toward me. Another way of exhibiting push or pull, when this particular case, it's going to be both, is with moving air, wind. We have a windmill here at our farm, and it pumps water for our pond, and the moving air. Now remember, wind comes from uneven heating of the earth by the sun, and that wind moves the blades of the windmill and causes it to pump water up for our pond. I'm going to use a different kind of moving air, the air from my lungs. This is a musical instrument called a harmonica. This particular one is a Hohner Marine Band harmonica, and when I blow on it, it makes a sound. And the blow is going to be a push. I'm going to push the air out of my body. Now I can also reverse that. I can pull the air the other way through the harmonica. You see it changes the tone of the instrument. This is a very good instrument actually for 4th grade. It's easy to learn, and there are a lot of different genres of music that can use a harmonica. Okay, another one that we might think about of using air would be to use an anemometer. Let me get that. Now, this is a toy anemometer. A real one would have a device on the stem here that would count the wind speed. But this is a toy one just for demonstration. I'm going to blow, once again, using air from my lungs and make it go around. So that's a force. That's a push. That's a push with air to make the anemometer go around. So remember, push is away and pull is toward. Okay, now the next one, you're really going to like this. This is a perfume bottle. It's got an atomizer in it. And atomizers work with the Bernoulli Principle. Now, you may be familiar with the Bernoulli Principle from when you take a shower. The Bernoulli Principle states that when fluid increases in speed, it lowers the pressure. So when you when you turn the water on in the shower, the fluid, the water in this case, is going very fast, and it lowers the air pressure in the shower, which causes the shower curtain to try to wrap around you. That's the Bernoulli Principle. Well, they also use it in atomizers. When I push the button on the top, there's a push. It's going to push air out the front of the atomizer. When that air goes really fast, it lowers the pressure up here, and that's going to cause the perfume to push up the tube. So I'm going to push it, and I think you're going to be able to see it over my shoulder and the poster behind me. Did you see that? So that was the Bernoulli Principle that allowed that to happen. I pushed here, that was one push, but the other was the push of the perfume up the tube in response to the Bernoulli Principle. All right, and let's see, oh, a saw. Now here's a great one right here. We all know about sawing. We can saw wood. This particular blade actually saws metal, but the way it works is it works with two forces, push and pull. So when I push it away and then back, when we pull it back. So away and toward, push and pull. So there's the forces using a saw. All right, let's see if we got something else. And I've got one right here that I think that you're very familiar with. You've probably done it. Oh, well. You've probably done this 10,000 times since March. Pull a Lysol wipe out of the container. So that's an easy force. It's a direct contact. I did that with my hand, and that was a pull. I pulled it out. All right. Now, this may not mean so much to the kids in Kansas, but it means a great deal to the kids here in Texas. This is Big Tex. He's the mascot of the State Fair of Texas, and we weren't able to have a state fair this year because of the pandemic. But this is Big Tex drink, and this is left over from a year ago when we did have the State Fair of Texas. He has a straw back here. So I am going to put pressure from my mouth to draw the water up through the straw into my mouth. I'm going to pull it toward me. Okay, so there's Big Tex, and I pulled the water out of the water container. All right, so let's review our words right here. We know that forces cause change. Let's talk about some of the changes we saw. The push from the chicken caused the change of the chicken moving position from inside the chicken to the egg, moving from inside the chicken to outside. So that was a push that ended up in that change, in that regard. Okay. We're going to remember that energy is the ability to do work, and we get that energy from lots of different places. The electromagnetic spectrum, we get it from gravity, we get it from magnetism, light and heat, and nuclear, and electrical, and motion, and elastic, and gravitational. I think that's about it. But if you have any questions about push and pull and the fact that forces cause change, Mr. Broughton will be glad to answer those. Thank you.
Thank you, Mrs. Fuller. We got two questions, both from Amanda Arnold Elementary and both from Carlene. Her first question was, how many bones do polar bears have? And I had to look that one up online, and the first resource that I found said 210 bones are in an adult polar bear. But polar bears also do push and pull things. So after they catch a seal, they'll bite onto it and pull it apart to eat it. And then her second question was, can you play an instrument backwards? A harmonica, yes, because you can exhale into it to make a noise and inhale and pull air back into your body to make a noise. But other instruments like a flute, I don't believe you could play that one backwards. So as far as I know, it's just a harmonica. All right, now we're going to explore another force, which is gravity, with Ms. Ramirez.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about gravity. So gravity is just the force that pulls things down. So if you take a moment to stand, push your chair in, and then try and jump as high as you can. Gravity is going to be the force that pulls you back down. So today we're going to be doing an experiment today with a pendulum and gravity. But before we get into that, let's talk about the history of the pendulum. So a scientist named Galileo was sitting in church. This was around the 1500s. So he was in a cathedral, and he happened to look up. He noticed that the chandeliers were swinging back and forth. Now, he noticed some of the chandeliers were moving kind of slow, and then some of them were making big swings. So being the good scientist that he was, he thought, why is that? So he devised an experiment. And because he was a very well-known scientist, we now know him as the father of experimental science. So one of the things that he devised was something similar to what we now know of as a pendulum. So a pendulum is just a device that swings freely based upon gravity. So let's take a look at an example of a pendulum. So I'm going to slide my little pendulum box over here. So here's a pendulum. You guys know pendulums. Think about your playground. What would be an example of a thing that you play on at the playground that resembles a pendulum? So a swing. So here's an example of a pendulum, and it has a couple of parts. So the first part a pendulum has is the support beam, and then it has an arm. So the arm is what allows it to swing like this. And then the bottom of my pendulum, I have a weight. This is just a washer, but what's at the bottom of a pendulum we call a bob. So my bob happens to be a washer. And the forces that are acting on a pendulum, we said was gravity. So gravity is the thing that pulls things down. So when I take my washer and I raise it up and I release it, gravity is going to be the force that's trying to pull it back down. Now, it will eventually stop moving because of gravity, one, trying to pull it down, but also there's some friction. So friction is a force that slows motion down. In this case, the washer is encountering some air resistance that is trying to slow it down as it's moving. Now, this also brings us to a very important concept, and that is inertia. So inertia is just the statement that objects in motion are going to stay in motion unless a force stops it. So if there were no forces acting on this pendulum, it would swing forever. But we know that there are forces acting on it. We know we have gravity, and we know we have friction that are acting upon the pendulum, and that is why it eventually stops swinging. So we are going to do a quick little experiment. We're going to investigate how string length affects the number of times a pendulum will swing within 15 seconds. So go ahead and make a hypothesis. What do you think is going to happen? So what string length will have the most swings in 15 seconds? Is it the short 5 centimeter string, the middle 10 centimeter string, or the long 20 centimeter string? So which one will have the most swings in 15 seconds? And think about why. So I'm gonna set my timer for 15 seconds. I know it's gonna be a little hard for you guys to see what's happening, so I'm gonna count it out as the pendulum completes each swing. And each swing is defined as, if I start the pendulum here, it's gonna swing forward and then it's gonna go back. When it goes back, that's the completion of one swing. So I'm going to go ahead and start our timer, and then we'll start counting. We're going to do the small string first at 5 centimeters. So my timer is going, and let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So it's about 26 swings for that short string. So let me go ahead and write our notes down on our little chart here. So for our short string, it has 26. Now we're going to go ahead and do the long string just to save some time. So I'm going to start it off. I'm going to start our timer, and we're going to count again. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And I'm going to go ahead and stop it there. So it was about 18 swings for our long one. Now, to save time, we're not going to do the little middle one, but if you were going to do this experiment, without doing the experiment, what would your hypothesis be? So if this one swaying 26 swings, this one swaying 18 times, how many times do you think the middle one would swing? So I put our data in a little chart that looks like this. So I only did one trial, but as a scientist, you would always do at least 3 tests to make sure your results are accurate. But due to time, we're just going to do one today. So the 5 centimeter one had 26 swings in 15 seconds, and the 20 centimeter one, the longest one, had 18 swings. So how can you explain, how does string length affect the number of swings the pendulum will do? So think about that question. And then the next thing we're going to talk about really quickly is how our animals use pendulums. So out here at the Environmental Center, we have a lot of chickens. I have a chicken. Her name is Pepper, and she's a blue silky chicken. So here she is right here. When she's outside, she loves to go and play on her swing. So here's her swing right here, and it works based on the same principles as a pendulum. It moves because of gravity, and it eventually stops moving because gravity is trying to pull it down, and there's also air resistance as well. So I'm going to share my screen with you guys, and I'm going to show y'all just a quick little video of some chickens on swings, as well as some other animals. I didn't mean to press that button. Let me start that screen share one more time. So here's our little presentation. We'll see if it plays full screen. If it doesn't, we'll just go back to the little screen. So here's the chickens on the chicken swing. So think about how do forces such as pushes, pulls, and air resistance affect the swinging motion. So chickens like to be high up because they're prey animals. There's lots of things that would love to eat them. So oftentimes the chickens out here, we'll see them perched on a railing or on cars or on tree branches. And then here's a cute little video of a fainting goat. So see what happens when this little goat jumps on a swinging bench. And he falls right off. So the reason that he's falling off is because fainting goats, it's a hereditary condition. When they get startled, and there's his cute little cry, when they get startled, their muscles tense up and they stiffen so they can't move. So I thought that was a cute little video. And then here's a video of a squirrel on a homemade obstacle course. So something that you guys could do at school or at home for a STEM challenge is create your own obstacle course. The tower that the squirrel is climbing on is just made out of soup cans. You can make your own swing using sticks or boards and yarn. And you can observe how squirrels and other wildlife use that obstacle and think about what forces affect them as they're moving around it. So I like to watch wildlife. And then a little reflection question for you guys is to find examples of at least 3 pendulums in your everyday life and think about what forces affect their motion. So here we just have an example of a seismograph. A seismograph actually utilizes a pendulum, and a seismograph is a tool that helps to detect earthquakes. So I'm going to stop sharing my screen because we are about out of time. So let me move my picture out of the way. So I'm going to stop sharing, and we're going to go ahead and pass it back to Mr. Broughton, and he's going to answer any questions.
Thank you, Mr. Ramirez. The question that came in was from Jude from Amanda Arnold Elementary. And the question is, how does the Earth stay in its place? It is the sun's gravity. The sun's gravity holds the Earth in its orbit as it revolves around the sun every year and keeps it from flying off into space. So great question, because we were just talking about gravity. All right, now we're going to talk about a new force which opposes motion, and that is friction.
Hello, welcome to my classroom students. My name is Miss Nash, and today we're talking about friction, which is really important. And I had never really thought about it myself very much. But it turns out that without friction, we couldn't walk around, we couldn't pick anything up, we couldn't stop the car once it started going. So friction, there are 2 kinds of friction, static and kinetic. So static just means before anything's moving. When something's just a big box maybe, sitting there on a table. And the force, there's no force, the force on it and the force of friction are equal. It does not move. So if I have something heavy, like my boot here, I have a heavy boot, if I just push on a little bit, it won't move. I have to push harder and then it starts. Now it has kinetic. So once this force gets bigger than this force, then it starts moving. And then we're talking about kinetic friction, which means the friction is operating once something is moving. Now, friction keeps things from moving, otherwise they'd just be sliding all around or floating away, and it stops things from who are moving from continuing to move. The amount of friction is dependent on force, the amount of force exerted, the surface on which it's sitting, the object, and the weight of the object. So we can kind of think about that in our everyday life. We know that if I have 2 little boxes here, one empty, one full of books. If I want to move those 2 boxes, if I use the same amount of force, I can move this one easily, but not this one because it's got all these books in it. So there's more friction force on this box than this one. Okay. So we know that from our everyday life. But once we get that heavy box moving, then we can move it fairly easily. Now the surface on which things are moving also has an effect. And I've got two little ramps I made here. One is just smooth, and one I put a piece of corrugated cardboard. So let's make a test. I have two styrofoam balls, so they're kind of rough also, so that may have an effect. You can think about that. Now, because they're round, they have only like one point of contact at a time. So that's why wheels and balls roll around really easily, where a square box, each same size, would not move as quickly. So let's see, which one do you think is going to make it down first? Take a guess, and there we go. So the one that came down the smooth ramp came down quicker. The surface was slippery. Think about an icy patch or a wet spot on the floor. You're liable to slip, okay? Because there's less frictional force. But interestingly, and just surprised me. I took these two little blocks. They're the same, they're painted, they're really smooth. And if I put them on my ramp, they don't move at all. There's not enough gravitational force to pull them down. So to get them to move, what can I do? Well, I can raise my ramp. So let me raise that ramp up. So as I raise the ramp, there's going to be more force of gravity, right? So now, let's see if it works this time. Let's see what happens. Who do you think is going to win this time? Actually, interestingly enough, the corrugated side goes down more quickly. Now, why is that? Try again. I kind of tied that time. But when I run that test over and over, more times than not, the corrugated side actually wins the race. And that's because even though it's smooth and it's just smooth, there's lots of kind of microscopic roughness. Okay. So the points of contact are actually more than on here. Because on this one, the top part's the only part that's in contact with this. So there's actually less contact here than on the flat one. Isn't that weird? You can try that yourself. Some kind of fun experiments to do. And I have a friend here to think about. Come here. I don't have a chicken. I have somebody that would like to eat their chicken eggs. Okay, I've got my friend here. My friend Red. So Red's a rat, snake, a corn snake. And kids come and they say, how does that animal move? So all of us move by pushing with friction against the surface. But Red is so smooth that it's hard to imagine how she moves over a very slippery surface. And indeed, it's really kind of hard for her, like on a flat table like this, it's hard. Let's see how she does on the ramp, or he does. Let's try it. See if I can get her. Okay. He's having a bit of a hard time trying to push himself up against the sides like that. It's kind of hard for him. He's doing it, but slow. Let's see. Thank you, Red. Let's see if he does any better on the corrugated. Really, Red? I'm sorry. Okay, is it working better for you? A little bit, maybe. Hard work. Okay, so I think you've done a little bit better. Not doing too well there either. Now on poor Red. So too slippery for Red. So on the bottom of the snake, see those scales on the bottom of the belly? They're kind of, they have a little kind of a ridge in them that can give him a little bit of a grip on rough surfaces. But I think this one's not quite rough enough. So friction is actually quite important. We use it to stop, we use it to start. So I'd like you to do a couple of things, go around the house and compare static friction and kinetic friction. So remember, static friction is things that aren't moving before they start moving, and then kinetic friction is once you've got them moving. And then you can run some little experiments of your own. And you can compare how hard it is to pull or push something across different surfaces. Is it harder to pull it across a floor, a flat floor, or a rug? Okay, so that's the force, surface, and weight are the three things you want to vary, okay, to make your little experiments. Okay, thank you. And if you have any questions, you can ask Mr. Broughton.
Thank you, Ms. Nash. The question that came in was, can snakes crawl backwards? And they can a little bit. You could, especially they can pull their head back if they need to, but they definitely prefer to crawl forward. That's how their scales are designed. So unless there's something wrong, you probably will not see a snake trying to crawl backwards. Maybe if it were being attacked, it would back up. Otherwise, you will only see them crawl forwards. All right, now we're going to move on to our last force of the day. It is magnetism, and that will be led by Mr. Monroe.
Good afternoon, students. My name is Mr. Monroe, and we're going to investigate magnetism. Now, that word magnetism, it describes a property that some materials have that they will attract steel, iron, and maybe a little bit of nickel. You might say to yourself, well, why is that so important? Well, I'm here to tell you, students, in our everyday lives, there are magnets that surround us. But let's talk about magnets for a little bit and discuss, or I will show you how they work. Now, magnets come in all different kinds of sizes. We have small ones, we have gigantic ones, and they come in different shapes. Probably the magnets that you're familiar with are like the ones I'm going to show you. For example, a bar magnet, a horseshoe magnet, and maybe a ring magnet. Now, they do come in different shapes. And, you know, when I first saw a magnet go to work and it was attracting a piece of iron, I thought, wow, that's magic. Well, it wasn't really magic. It was science. And it made me start thinking about, where did magnets come from? Who invented them? Who discovered them? And you know what? I don't think I ever found out who the true inventor of a magnet was, but I did read about several stories, several legends about how magnets were discovered in their natural form. Now, in their natural form, they're simply a rock formation. And that rock formation would be made up of rock material that look similar to this. In fact, this is a rock that is referred to as magnetite. Another name for it, it is called lodestone. And I could get into telling you the story, but I don't have time. You guys kind of look that up. There's some interesting stories about how this was discovered. Now, magnetite can be found all over the world. The closest deposits of magnetite to us here in North Texas are located in the state of Arkansas and in the state of Louisiana. Now, going back to the magnet, the bar magnet, the strongest areas of attraction, where the most force of pull is located, is in its poles. On the bar magnet, we have an N that stands for the North Pole. And on the bottom of it, we have an S that stands for the South Pole. The same way with the horseshoe magnet, S for South Pole, N for North Pole. And on a ring magnet, one side would be the North Pole, the other side would be the South Pole. That's where the strongest magnetic force is located. Now, another thing that I experienced with magnets was the fact that there's a lot of uses for it, but I can remember passing by a salvage yard or a wrecking yard where they collect all this metal junk, and I noticed that they use very large magnets to separate certain metals, to separate certain materials, because again, magnets are only attracted to steel, which Iron is used in the making of steel, iron itself, and a little bit of nickel. Now I'm going to run a little test here to see if that's true. In fact, I've got a Petri dish here. I'm going to put a nail. I'm going to put a screw. I'm going to put a very small ball bearing, which is a small bead-looking like object. A pop top from a soda can. Oh, let's see here. I don't know whether a magnet will react to this, but we're going to find out. This is a brad. And it's goldish in color, so I don't know about that. And I'm going to put some money in here. Let's see. I got a penny right here. I'm going to put a penny in there. And let's see, what else can I find in this pile of junk here? A thumbtack. How about just a rock? Drop that in there. And this weird looking paper clip. And then a regular looking paper clip. And I'm going to take, now listen, I want to share this with you before I do this test. You know, a lot of people think the bigger the magnet, the stronger the pull. That's not true. And we'll discuss that a little later on. I have a very small bar magnet. And as compared to this bigger magnet, guess what? This small one is stronger than this one. And it's the one we're going to use. So let's see what items it's going to pick up out of this Petri dish. It's picking up some. Wow. Let's see if it'll pick up any more. Look at that. It has picked up the nail, the ball bearing, the paper clip, the thumbtack, and it even picked up the brad, which is gold in color. So those items, that material that it has attracted, pulled up to it, guess what? Has either iron or steel or maybe a little nickel in it. What it did leave was a penny. And we know that a penny's made out of copper, so that wasn't going to be picked up. The pop top from a soda can is made out of aluminum. That's another type of metal that is not attracted to a magnet. And this weird looking paper clip is made out of plastic, so it wasn't attracted. And evidently, there is no iron or steel or nickel in this rock. It did not pick that up. Now, that is a pulling action, attraction. It pulls those items to it that have iron, steel, or a little bit of nickel in it. Now, sometimes they will even give a pushing action. For example, we know that it has the poles, North Pole, South Pole. If I take these two small bar magnets and I match the North Pole of this one to the North Pole of this one, we're going to see that they repel each other. They push away. I can't hardly put that together because they're pushing each other away. But if I reverse this and I take the South Pole and I match it to the North Pole, guess what? They attract each other, okay? So like poles, they will repel and push away. Unlike poles, will attract. And I want you to remember that because students, listen. You heard me mention that we use magnets in our everyday lives. Guess what? Magnets are used in the medical field. There's a machine that hospitals use. It's called an MRI machine. This machine is used to take images of the human body. They run a person's body through this machine and it's searching for things that might be wrong inside that person's body. Guess what? Magnets are used in that. At your house, in your home, that refrigerator, around the door of your refrigerator, there is a magnetic strip that helps that door close real good and seals it good so that warm air can't get into your refrigerator to spoil your food. Magnets are also used in computers. They're used in phones. They're used in doorbells. Even some of the games and toys that you're active with, guess what? There are magnets found in it. They're also used in generators, in power plants, and they're used to generate electricity. So magnets can be used to generate electricity. They're also used in electric motors. And I've got an electric motor. I want to show you guys how it works. This is an electric motor that I took from the pump that was in my aquarium where I keep my bullfrog, my pet bullfrog. And this pump is used to circulate the water And as its propeller is turning, it generates currents or water currents in there, making the water move, and it generates oxygen for my bullfrog. Well, let me go ahead and plug it up. And you can see that it is an electric motor that is doing some work. Now, how this electric motor is working is the simple fact that inside the electric motor, there is a stationary magnet that surrounds the little magnet on here, and it has a south pole and a north pole embedded inside there. And using the repelling action, the pushing away, and the attracting action, guess what? It makes the propeller constantly spin. Now, remember when I said that magnets, you can't gauge their strength by their size? This little bitty magnet that you see on the end of here, guess what? It's very strong. That's not a horseshoe. That's not a bar magnet. It's not a disc magnet, but it's a very small magnet, and it is very powerful. Look at that, how much stuff that it pulled out of this junk pile, okay? It's very strong. So it doesn't make any difference about the size of a magnet, but its strength is what counts. Now, students, listen. There are other uses. In fact, those of you who have been on camping trips with your family, maybe even hiking, guess what? When you go into an area where you're afraid you're going to get lost, wow, it's very important that you carry a little tool that we call a compass. A lot of people don't realize that that compass, that needle in there, is a magnet. Now, our planet, the planet Earth, has a North Pole and a South Pole. You guys knew that. Well, could it be that our planet is like a big magnet? How true that is. In fact, it is the largest magnet that we know of, okay? The North Pole is often referred to as the magnetic north. So I know that the direction of north from my lab, my classroom, is that direction, okay? So if I hold this compass up, I can see that the little red hand in here is pointing to the north, and it's being pulled by the magnetic north. It's kind of strong, isn't it? Because the North Pole is a long ways from here. Just to show you, I have created what I call a homemade magnet. I have suspended a bar magnet on a measuring stick, and it's suspended now. It's spinning around right now, and I'm going to kind of stable it from me moving it. Just stable it, and it'll spin a little bit. But eventually, it's going to find the north. We'll give it just a little bit of time to do that. Probably going to spin back that way now. Well, nope, it's going to continue there. And it's hopefully it's going to stop right about, well, it's going to go back again. It's working, it's trying to find it. And it just about has found the magnetic north. Now, if you're ever using a compass and you get close to another magnet, do you think that compass is going to work? I don't think so. Even if you're walking on top of a rock formation that is called lodestone or magnetite, guess what's going to happen? That magnet is going to go crazy. As you can see, magnets have an effect on each other. Well, students, that's about all the time that I have with you. Hopefully I've given you a little better understanding about magnetism. Now I'm going to give it back to Mr. Broughton. So if you have any questions, you might ask him.
Thank you, Mr. Monroe. The question that came in was, do animals use magnets? And yes, there are some species of birds that have a little bit of that natural magnet called magnetite in their brains, and that interacts with the Earth, which is a giant magnet, and helps them know which direction to fly when the seasons change, so they can fly south for the winter and north for the summer using that magnet in their brains. I'm going to share my screen with you. We're going to do a quick recap of what we did today. So today's field trip was all about force and motion. During this virtual field trip, students discovered that energy exists in many forms and can be observed in cycles, patterns, and systems. Students observed a descriptive investigation to explore the effect of force on an object. So we started off the day by investigating pushes and pulls with Mrs. Fuller. Next, we explored the force of gravity with Mr. Ramirez. Third, we explored the force of friction with Miss Nash. And we just explored magnetism with Mr. Monroe. Thank you so much for joining us this afternoon. We appreciate you taking the time to learn about force and motion with us. And we'd like to know what you think about today's field trip. You can let us know by going to www.tiny.cc/EEC feedback and filling out a short feedback form. We use your comments and suggestions to improve what we do here. We hope to see you again in about 3 weeks for our next field trip for fourth graders. Is going to be about earth science this time. And have a great rest of your day. We'll see you next time. Goodbye.